Students, in last class we discussed about the laser diode. This laser diode is a photo source or light source which is used at the transmission end of optical communication. In that laser diode we discussed about the construction working of laser diode. Today we will discuss about the optical detectors or light detectors which are used at the receiving end of the optical communication. These light detector or photodetectors are used to convert the light signal into electrical signal. These photodetectors, photodiode, pin diode, avalanche diode. Today we will discuss about the overview of photodetectors and working of photodiode. These photodetectors are light sensitive devices which converts the light signal into electrical signal. These are working the principle of photo absorption. These detectors or these circuits are absorb the light energy and which converts into the electrical signal. This photo absorption occurs if wavelength of incident photon is less than or equals to the cutoff wavelength, or it is equals to the 1.24 by energy gap Eg. So you can write lambda is less than or equals to 1.24 by Eg. We know for the visible light, the maximum wavelength is equals to 0.7 micrometer. From that we can write energy gap of the material in the photodetector can be written as Eg is less than or equals to 1.24 by 0.7. That means we can write it is equals to 1.77 electron volt. So while we are fabricating the photodetector, we are using the semiconductor material, which material energy gap is less than or equals to 1.77 electron volt for the visible light. Therefore, we can say semiconductor materials used with energy gap of 1.77 electron volt in the fabrication of photodetectors. Therefore, we can say at room temperature, the energy gap of silicon is 1.21 electron volt. It is closer to the 1.77. So, we can say the photodetectors can be fabricated using silicon also. Yes, these photodetectors performance can be judged by two parameters. One is quantum efficiency, another one is responsibility. This quantum efficiency is nothing but it's the ratio of number of electron hole pair generated per second to the number of photons incident per second. That means when your light fall on the device, it will generate the electron hole pair in the device. Yes, this photodetector converts the light signal into electrical signal. So the amount of light falls, that is number of photons incident per second. Based on that, number of electron and hole pair generated per second in the photo detector. Yes. So that quantum efficiency of photodetector can be defined as the ratio of number of electron and hole pair generated per second in the photodetector by applying the number of photons incident per second on the photodetector. So we can write number of electron and hole pair generated per second can be written as electron and hole pair created in the photo device means it generates the current, that is nothing but photocurrent. So we can write it is equals to I suffix pH by E. So it indicates the photocurrent, and number of photons incident per second, it is nothing but photon power. So we can write it is equals to P opt by HF. So from that we can write quantum efficiency can be written as IPH into HF, where H is the flux constant, F is the frequency of photons, and P opt into E. So here IPH is the current due to the photo excitation or current due to the generated whole electron and hole pairs in the photo device, and P opt is incident optical power, the amount of optical power incident on the photo device. And second parameter is responsibility. It is related with the R. So it is nothing but photo current generated per unit optical power. So we can write R equals to IPH by P opt. From that we can write quantum efficiency eta equals to IPH into HF by P opt into E. So IPH by P opt is replaced with the responsibility R. So we can write eta equals to quantum efficiency equals to R into HF by E. From that we can write F equals to C by lambda. So we can write R equals to Ne by HF or Ne by HC into lambda, eta into E by HF equals to eta into E by C by lambda. Here eta is the quantum efficiency, E is the charge of the electron, and H is the Planck's constant, C is the light velocity, and lambda is the wavelength of photon. These are the two parameters. Based on the two parameters, we can judge the performance of the photodetector. Yes. Next, we will discuss different types of photodetectors, that are photodiode, pin diode, avalanche photodiode, and solar cell. There are other photodetectors also there, that are pure semiconductor and phototransistor are also there, but we are discussing here only these detectors. This photodiode is a PN junction diode which is fabricated from the silicon. This photodiode having two terminals that are named as anode and cathode. It is looking like normal PN junction diode. In this symbol, we had a two arrow marks inside the diode. That means light falls on the diode. So it is a photosensitive device. When light falls on the diode, it generates the photo current. Yes. So it is a photodetector or light sensitive device, and this converts the light signal into electrical signals. Yes. And it is always operating in the reverse bias. Why? Because we may connect in the forward bias also. When we connect in the forward bias, what happens? When we connect in the forward bias, the depletion region is very small between the P and N type materials. Yes. When light falls on the junction, what happens? Electron and hole pair created, current will generate. Yes. So the current will generate in the photodetector more due to the forward bias only. So we cannot get the more current. We cannot identify the current due to the light intensity or light falls on the junction. Yes. So in forward bias, we know the current is in milliamperes. To get the current due to the light intensity, we are connecting that photodiode in reverse bias. If I am connecting a forward bias, then what happens? The depletion region width is very small, so the current will produce due to the drifting of electrons and holes as well as light intensity, and this electron to hole pair generation is very small compared to the this forward bias supply. So it is very difficult to identify the current due to the light. So in forward bias, it is negligible current due to the light. So we cannot notice or we cannot identify that current due to the light intensity. Yes. So the resistance of forward bias diode is not affected by the light or photon energy. Yes. So to have significant effect of light on the current and operate the photodiode in the reverse bias. Yes. So we are connecting this photodiode in the reverse bias. The negative terminal of the battery is connected to the anode, that means p-type material, and positive terminal of the battery is connected to the cathode, that means n-type material. So we know in reverse bias, the p-n junction offers the large depletion region. Here we can identify the depletion region width is W, and I mentioned the L suffix n and L suffix p. It is the diffusion length of electrons and diffusion length of holes. Yes. So now it is in the reverse bias, and that arrow marks indicates the light falling on the junction. So when we are connecting in the reverse bias, when there is no light falls on the p-n junction, that what happens? The minority charges are moving from p-type material to n-type and n-type to p-type. That means the minority charge carriers in the p region are electrons and minority charge carriers in the n region are holes. When there is no light or the junction is in reverse bias, it offers the large depletion region with the minority carriers in the p region are moving into the n region. The minority carriers in the n region are moving into the p region. Due to the mobility of minority charge carriers, small amount of current will flow. That current is reverse saturation current in the normal p diode. But coming to the photodiode, when there is no light fall on the photodiode, say that reverse saturation current will flow in this photodiode. This current is called dark current. So when there is no light, it is a dark. Yes. So even there is no light, the small amount of reverse oscillation current will flow in the photodiode because it is in the reverse bias. That reverse oscillation current is called dark current. It is represented with the I naught. Yes. When photodiode is illuminated with the light uniformly, what happens? Or when light falls on the photodiode, what happens? That photon excitation occurs. That that means we are supplying the sufficient thermal energy to the P and N type materials. Yes, when light is falling on the diode, we are supplying the thermal energy to the P and N type materials. That means these covalent bonds in the P and N type material are breaks, and it creates the new electron and hole pair. Yes, so these photo-generated electrons in the depletion region of p side will drift towards the n region because of electric field. Why? Because it is in the reverse bias. Yes. So in reverse bias, it has the large depletion width. In this, we are having the immobile charge carriers that are positive ions and negative ions. So it offers the large electric field. Yes. So when light falls on the photodiode, it generates the new electron and hole pair. These photo-generated electrons in depletion region of p side will drift towards the n region because of electric field. Similarly, these photo-generated holes in depletion region of n side will drift towards the p region of electric field. P region because of the electric field. And the photo-generated electrons within a distance ln, that means depletion length of electrons from depletion region will diffuse into the depletion region, then they enter into the n region. Yes, photo-generated electrons within distance of ln, it is about diffusion length of electrons. So electrons in the p region will not recombine with the holes. So it will travel a very small distance. The distance is diffusion length. How much distance that electron can travel without recombining recombining with the holes? Yes, that is nothing but diffusion length. So these photogenerated electrons within a distance of ln from depletion region will diffuse into the depletion region, then they will enter into the n region. Yes. Similarly, that photo-generated holes within a distance of Lp. So, photo-generated hole which is generated in the distance of Lp away from the depletion region will diffuse to the P region. Yes. So, we can say the current is due to the drift and this diffusion length Ln and Lp. So, here we can say current is due to drift process, another one is diffusion process. Yes. So even in the reverse bias also we are having the drift and diffusion. Diffusion means, so when concentration gradient is present, then the charge gases are moving from higher concentration to lower concentration. Yes. So these photo generated carriers which are at a distance is always greater than the either it is a Ln or Lp from the depletion region will recombine and they will after. So after the diffusion length of electrons or diffusion length of holes, they will recombine with the opposite charge carrier and they will disappear. Yes, so they do not produce any current. Clear? The suffix L be the optical generated rate. That means new electron hole pair generation rate. So we can write IL drift equals to E into GL into A into W. So here E is the charge of the electron or hole. So GL is the optical generator rate, A is the area of the junction and W is the depletion width. Similarly we can write IL diffusion. So it is equals to E into GL into A Ln plus LP. So the diffusion is the charge carrier is present in the length of Ln and Lp only. That's why I written E into Gl into A Ln plus Lp. So total current generated can be written as IL drift plus IL diffusion. So we can write is equals to IL equals to AEGL into W plus Ln plus Lp. This is the current due to the light only. Yes. So the overall current through the diode can be written as what we can write. So I equals to I naught into e power v by eta vt minus 1 minus IL. So this is the diode current equation and minus IL is the what about? It is current due to the light. Current due to the light. So now we are operating the photodiode in the reverse bias. So we know that V is negative value. So applied voltage V is negative value. So we can write E bar V by Vt can be written is almost equals to 0. So we can write I equals to I naught 0 minus 1 minus IL. So we can write I equals to minus of I naught plus IL. Yes. So here we can observe the photodiode VI characteristics. So in forward bias it is normal diode characteristics only. Coming to the reverse bias, so initially it offers the very small amount of leakage current or reverse saturation current. When there is no light, it is nothing but absence of light. This current is called dark current. It is represented with the I naught. Yes, when light falls, what happens? The current also increases. So we can observe the different G1, G2, G3, G4. So G4 is the G1, G2, G3, G4 are the electron hole pair generation. Electron hole pair generation. This electron hole pair generation will increase based on the intensity of light falls on the photodiode. So with increasing the light intensity, generation rate will increase and IL also increases. Yes. So this is called photoconductive mode. So photodiode is operated in the reverse bias because of to identify the to notice the current due to the light intensity or light falls on the photodiode. Why? Because the photodiode is converting the light signal into the electrical signal. Yes, if I'm operating in the forward bias, what happens? The current will produce due to the forward bias voltage as well as light intensity. Yes, so the current produced due to the light intensity is very small compared to the forward bias voltage, so we cannot notice that current. To identify the or to notice the current due to the light intensity, that's why we are connecting the photodiode in the reverse bias. Yes, when we are increasing the light intensity, the new electron hole pair generation is also increases. Then the current due to the light also increases. That's why we are connecting the photodiode in the reverse bias. Yes, photodiode is operated in the third quadrant, that means in reverse bias, then it is said to be photocorrective mode. If photodiode is operating with the fourth quadrant, then it is said to be photovoltaic mode. Such photodiode is called solar cell. We will discuss this solar cell in the next class. In this fourth quadrant, what happens? So V and I are negative values. V and I is negative value, which implies that the device is acting as a source of energy. Source of energy. That's why we are using solar cell as a source of energy. Yes. When light intensity increases, what happens? The drift component of photocurrent will increase immediately, but diffusion component responds slowly because it requires the development of concentration gradient. So diffusion process can present when concentration gradient present. Yes, when light intensity increases, diffusion component responds very slowly because it requires the concentration gradient. Hence, we can say diffusion component is also called as delayed photocurrent. Yes, therefore, to to improve the response, or if faster response to change the light intensity is desired, then drift component should be made greater than the increase in the depletion region. Yes, so we must increase the depletion region. Yes, to to increase the depletion region, we are fabricating the we are including the or we are adding the extra region or intrinsic region in between the p and n type materials. Yes, so such device is called pin diode. P region, intrinsic region, and n region. Why we are adding this one? When light intensity falls, when light intensity increases, the diffusion component responds slowly because it requires the development of concentration gradient. Yes, therefore, a faster response to change the light intensity is desired. Yes, so we need the faster response if light intensity is increased. Yes, so then what happens? Drift component should be made greater by increasing the depletion region. The better way of increasing the drift current is including the including the intrinsic region between the p type and n type materials. So such device is called pin diode. So we'll discuss about the pin diode in the next class.